Hey college physics students, this is the WorkEnergy lab. So first of all, let's start with what we need for this lab. We need some rubber bands. I want you to try to find they come in various sizes. Here's a 1/4 inch, here's an 1/8 of an inch wide, 1/8 of an inch wide, and skinnier yet, they come in 1/16 of an inch. I don't have one here. They also come in different lengths, of course. The length of the rubber band's measured by laying it out on a ruler in an unstretched way and measuring the length. So I want you to find a 1/4 inch rubber band that's about 3.5 inches long when you lay it out. 3 or 3.5 inches long. The rubber bands that come on broccoli work pretty well. Here's one here, but it broke, as you can see. They're not real strong. So, by the way, a 3.5 inch long, 1/4 inch wide rubber band is called a number 64. I think a 3 inch long is a 63, and a 2.5 inch long is a 6. Anyway, let's not get into too much details of the rubber band. And what else do we need? Here's some 3 inch long. Here's some 3 inch long, 1/4 inch wide rubber bands. So try to find one that's a number 64, 3.5 inches long, and a 1/4 inch wide. All right. What else do we need? We need our force probe. Let me get my camera going. I'll have to keep turning my camera on throughout this because, as I pointed out, it turns off every 2 minutes. So we need our force probe. We need a ruler, some tape, a paper clip, tape measure. You know, you can get by without a tape measure. Now, here's a number 64 right here. It's 3.5 inches long and a 1/4 inch wide. So that's what I'm going to use. And so we need, and our safety glasses. So I'm going to get my safety glasses on right away because we're dealing with stored energy. You know, when you deal with stored energy, things can go wrong. So have your safety glasses on. And if anybody's helping you, have them have some kind of eye protection as well. All right. Well, what are we going to do? Well, we've all flicked a rubber band before. You know, you stretch it. I'm going to shoot it at the camera here, see if you can see it. Went pretty fast. It was a blur across the screen. Let me shoot a couple of them, see what happens. It's going too fast for the camera to see it. Okay. If you ask a physics teacher to describe what's happening when you flip a rubber band, here's what they'll say. They'll say, and this is based on the ideas that we talked about in chapter 6. They say, when you stretch this rubber band, you're doing work, okay? That work in joules is stored in the rubber band as elastic potential energy. This rubber band, since I did work on it, if I did 5 joules of work, it's got 5 joules of potential energy stored into it. Now when I release it, just shot way over there, when I release it, that potential energy in the rubber band gets converted into kinetic energy of the rubber band, and it goes flying off with kinetic energy. So we're going to test that explanation. We're going to, because this is physics, we do measurements here. We don't just shoot off our mouth. We actually measure things to see if they come out. So we're going to measure the amount of work we do to stretch the rubber band a certain distance. Then we're going to fire the rubber band, and by determining how far it went, if we shoot it horizontally, like we did in projectile motion, by determining how far it went and how much time it took to drop from the height at which we fired it, we're going to calculate the velocity and the kinetic energy of the rubber band and see how those two numbers compare. How does the amount of work I did to stretch it compare to the amount of kinetic energy that I get out of it? Okay, so to measure the let's get down to the measurements. So I'm going to take my ruler and set it out here on the table, and I'm going to tape it down on the inches side of the ruler, because I don't need to read the inches. And so it stays put. And then I'm going to lift it off the table a little bit by putting something under it, maybe a paper clip or something here. Lift it off the table a little bit. And then I'm going to take my rubber band. Here's my 1/4 inch, 3.5 inch long, number 64 rubber band. And I'm going to hook it on the end of the ruler. Now remember, the formula for work in chapter 6 was force times distance. Well, we can't use that formula here. See, I've got the rubber band hooked at the end of the ruler. Hooked at the end of the ruler so I can stretch it along here. I want the ruler off the table some, so I'm going to use 2 paper clips to lift it off the table. I don't want the rubber band rubbing on the table. Okay, so I can stretch the rubber band along the ruler here. Okay, now I'm going to take a paper clip. Oh, I need another paper clip now. There's one. I'm going to take a paper clip and hook it on the end of my rubber band for now. So I have a hook on it. And then put my rubber band back underneath the end of the ruler. And I'm stretching it along the ruler. Get the idea? Okay, now I'm going to take my force probe and get it so I can see the scale. All right. Camera back on. Get the force probe so I can see the scale like this. So now I can pull on my force probe and it stretches the rubber band. Okay, so as I said, in chapter 6 we just took force times distance in order to find the work done. We can't do that here because the force that we exert on the rubber band is changing. We have to exert more and more force to stretch it further and further. So we have a varying force. They just touched on that at the end of the chapter, unfortunately. So what we need to do is we need to take some data. How much does the rubber band stretch with 1 Newton, 2 Newtons, 3 Newtons, 4 Newtons, 5 Newtons, 6 Newtons force? How much, and make a graph and find the area under that graph. So I'll show you how to do that later. Let's just worry on getting the data right now. So first I'm going to apply 1 Newton of force to this. And that stretches it, that just kind of pulls it tight, so it's not to give us a decent reading of the length. It doesn't really stretch the rubber band very much. It just kind of takes the slack out. So I'm pulling with 1 Newton force, and I'm going to read the distance along the ruler, and I get 8.8 centimeters. Okay, that's going to be my starting point. So I want to measure how much the rubber band stretches, not what its length is. Actually, you do need to know its length for another part of this calculation, and I'm going to take this as the length of the rubber band because it's along the ruler, and I get, I'm going to take the length of this rubber band to be 8.8 centimeters. You need to write that down to put for the length of your rubber band. If you look at 8.8 centimeters, that's about 3.5 inches. This is a number 64, 3.5 inch long rubber band. Okay, so now I'm going to apply 2 newtons of force and see where the end of the rubber band is. So I'm going to pull this out to 2 newtons. And the end of the rubber band now is at 9.2 centimeters. So the difference from that starting point to 9.2, I forget what it was, 8.8 to 9.2, the rubber band, with 2 newtons of force, the rubber band stretched, whatever the difference in those two numbers is. You need to write these numbers down. I've already taken these measurements, so I'm just showing you how to do them. Then I pull with 2 newtons. No, 3 newtons is next. I pull with 3 newtons. Now the end of the rubber band is at 9.9 centimeters. So the difference between my starting point at 1 newton and 3 newtons. See, I have to exert more and more force to stretch the rubber band a certain distance. So I can't, my formula for work, force times distance, that only works for a constant force. In this case, the force is changing, so I wouldn't know what number to put into my force times distance formula. Okay, so you write that down. You write down where the end of the rubber band is now, subtract it from the starting point, and that's how much it's stretched. So what you want, your data is going to be force in newtons and amount of stretch. We'll call it the stretch, not the length, the stretch. Okay, then I pull with 4 newtons, and the end of the rubber band's now at 11 centimeters. So the difference between that and my starting point, the beginning length, is how much it stretched. And then I pull with 5 newtons, and now it's stretched, now mine is reading 12.5 centimeters, and so on, up to 6 newtons. So we're going to take the amount of stretch to be 0 when you pull with 1 newton. That just kind of takes the slack out. Then we're going to measure how much it stretches when you apply 2 newtons, 3 newtons, 4 newtons, 5 newtons, and 6 newtons. That's going to give us, well, 1 newton will be 0 stretch. Then we'll have 2 newtons, 3 newtons, 4 newtons, 5 newtons, 6 newtons. So we're going to have 6 data points. Force and stretch. Okay, you need to convert that to meters. Now I'm going to let's do all the measurement part first. Then we'll go find the work. All right. Okay, for the next part, to measure the kinetic energy, I'll show you. We'll have to make a graph to calculate the work and find the area under that graph. But I'll show you that after we get to the second part of this. Okay, my maximum stretch, I forget. Let me put this back in here and find out. My maximum stretch was about, I don't know, 5 centimeters, 5 or 6 centimeters, I think. Pull with 6 newtons. My maximum stretch was about 6 centimeters. You'll have a better number than that. So it's about 6 centimeters. So now I want to find the how much kinetic energy I'm going to get when I stretch the rubber band 5.5 centimeters, or whatever the maximum stretch is for your rubber band. I want to see how much kinetic energy I get from that. And what I'm going to do is take my ruler off. I'm going to hook the rubber band on the end of the ruler, and I'm going to hook the rubber band on the end of the ruler, and I'm going to pull it back 5 centimeters, 5.5 centimeters, or in your case, whatever the maximum stretch is. Then I'm going to shoot it horizontally. You need a lot of room for this. You might have to do it outside. I'm going to shoot it horizontally, and I need to measure 2 things. I need to measure how high off the ground it was when I shot it. That's going to determine the amount of time it took to drop to the ground. And I want to measure the horizontal distance the rubber band went, which could be 10 feet or so. So you might have to do this outside or across the diagonal of your room, clear a space. So I need to measure those two things. That's going to allow me to calculate the velocity of this rubber band when it left the ruler. And so consequently, 1/2 mv squared, once I determine the mass of the rubber band, which is explained in the write-up, then I can calculate the kinetic energy. And I want to compare the kinetic energy of this rubber band with the amount of work I did to stretch it. Okay, so now I'm going to move on and show you how to do the work calculation. Okay, physics students, I've made a graph here. I've taken my data. I've got force on the vertical axis, force versus stretch. I've got force on the vertical axis and stretch in meters, so you got to convert your centimeters into meters, and meters on the horizontal axis. Now we don't want to fit a straight line to this curve because it's not a straight line by any means. You can see that it's kind of bent over. It's a straight line for very small displacements. It follows a straight line, but then it curves over. What we want to do is find the area under this imaginary curve here. If I drew a curve like this, I'd have an area, all this area under the curve, and that's going to be the work done. That's the formula. That's the way that you have to calculate work when you have a varying force, as you do in a spring or a muscle or many things in life. When you stretch them, they exert varying forces depending on how much they've stretched. So that's how you have to calculate the work, by finding the area under the curve. That's done mathematically with calculus. We don't need to use calculus because we have this graph here. So I want to find the area under this curve, and here's what I'm going to do. I'm going to click and drag over all my data points. This one had a maximum stretch of 12.2 centimeters, so this is a totally different kind of rubber band. This is a different rubber band I was trying. So this data isn't going to do you any good, so don't try to copy it, please. And then you click on this little graph thing down here, and you do View Integral. That's what they call the area under the curve in calculus. That's called the integral. So you do View Integral, and it tells you the area is 0.474 newtons times meters. We know a newton times a meter is a joule. So the area under the curve is 0.474 joules. Now you're not going to get a number this big because I was trying a really big rubber band. Really just a different kind of example. You're going to get something, if you have a standard number 64 rubber band, you'll get about 0.2 or 0.3 joules here. Anyway, so that's the amount of work I did to stretch the rubber band, in this case to 12 centimeters. And then I shot it and measured the kinetic energy. I got a lot of kinetic energy with this, so the rubber band went, to measure the distance it went, you'd have to go outside for sure. Anyway, so that's how you do the work calculation. Then you do the kinetic energy calculation as described in the lab and compare those two numbers. And that's it.